let me welcome you all to this SFI community lecture, and let me thank Thornburg Investment Management very much for their support of this series. We're very grateful for that. So, in fact, I know in advance, even without the help of time travel, that this is going to be an excellent talk, because Seth is not just a gifted scientist, but also a gifted explainer of science. For many years, energy was the key quantity in physics, and physics was about the transformation of energy from one form to another. And now we've recognized that information, in many situations, is equally important or more so. And this raises wonderful questions like, how can quantum physics help us transform information and perform computation in new ways, both in the quantum computers that we will hopefully design and build, but also in the larger universe in which we live? And Seth has been a key figure in drawing these connections. Seth got his bachelor's degree from Harvard, a master's in philosophy from Cambridge University, and his PhD from Rockefeller. He did postdocs at Caltech and here in New Mexico at Los Alamos. And he then joined the mechanical engineering department of MIT, which luckily is an institution which defines mechanical engineering quite broadly. And in fact, Seth calls himself a quantum mechanical engineer. A quantum mechanic. But you need your overalls to really be a quantum mechanic. Anyway, he is a fellow of the American Physical Society, the director of the Keck Center for Extreme Quantum Information Theory at MIT, and we're very proud to say is also a member of the external faculty at the Santa Fe Institute. So as I mentioned before, he's been a key figure really in all aspects of physics and information. He proposed the first physically feasible model of a quantum computer. He's studied the power of quantum communication to convey information, including the puzzle of what happens to information when it falls into a black hole. He's shown that quantum computers could vastly speed up our ability to solve problems in artificial intelligence. And he's studied quantum effects in photosynthesis, showing that plants use quantum physics to gather energy more efficiently from the sun. His book, Programming the Universe, is a lovely meditation on the interplay of information, computation, physics, and life. And I think we're all in for a treat. Please welcome Seth Lloyd.
It's a great pleasure to be back here. This is a second or third time I've given these public lectures for the SFI. I actually have a question about how people have heard about this. Who have heard about this via the SFI website or is affiliated with SFI? Great, and who read about it in the paper? All right, and who heard about it on the radio? Okay, and who heard about it from all three? You're the real quantum mechanical people in the audience, doing all three at once. So I'm here today to talk to you about what is, let's not mince words, time travel. Time travel is a subject that has occupied human beings for thousands of years. The very first time travel story I've been able to uncover is from the Hindu epic, the Mahabharata. And in this story, a king goes to visit Brahma in his palace in the sky, and they have a ripping good time together for about a weekend. And he goes back and he finds that countless eons have passed, and everything that he knows has turned to dust. And then there's a beautiful Japanese story about time travel called Urashima Taro. Urashima Taro is a fisherman, and one day he finds a turtle on the beach that's stuck in a fishing net. And he frees the turtle and sends the turtle back into the sea. And a few days later, a kind of turtley-looking but very beautiful woman shows up and invites him to the palace of the Dragon King under the sea. And Urashima Taro accepts. They go off to the palace of the king under the sea. She is a princess. She is indeed the turtle whom he saved from the net. They have a ripping good time. In fact, they have such a good time that they get married and they have children. And after a couple of years, Urashima Taro says to his wife, I'd really like to go back and visit my parents. I haven't seen them for a couple of years. They might be worried. She says, that's not a good idea. He says, no, I really would like to go visit them. She says, it's really not a good idea, trust me. He says, I insist on going and visiting them. She says, okay, don't tell me that I didn't tell you so. And she gives him a beautiful box covered with shells and mother of pearl. And she says to him, go back and take this box, but whatever you do, don't open the box. Yeah, you can kind of see where this kind of thing is going. So Urashima Toro goes back. He goes back to his island, and everything looks strange. Not only can he not find his parents, he can't find the village that he lived in. It's gone. Nobody knows him. The people are speaking in a kind of funny dialect. He doesn't know what's going on. And finally he finds this temple. And in the temple there's a monument that says, to Urashima Taro, lost at sea 300 years ago. And he goes crazy. He realizes what's going on. And while he's so obsessed and upset, what do you think he does? Yeah, like a fool, he opens the box. And out of the box comes this white mist that envelops him, and he turns into an old man and dies. Yeah, and the moral of the story is, no, it's listen to your wife. Listen to your wife. And in case you don't believe this, so in the beautiful retelling of the story, the first retelling in English by Lafcadio Hearn from the end of the 19th century, he says, and I have been to the temple in Yokohama where this marker memorializing Urashima Toro is, though I went to go try to find this marker and I couldn't find it. So there's a beautiful, in Irish legend, there's a story about O'Shan, who is the son of the famous Irish hero Finn McCool. And O'Shan meets a very beautiful woman, a fairy, who invites him to come with her to the palace of the king of the fairies. And they go have a raucous weekend partying, they fall in love. Do you detect a similarity in these stories here? Anyway, so they get married, the O'Shan and this beautiful fairy. But eventually he says, oh, I need to go back and visit my family. And she says, okay. And she gives him a magic horse to ride back. And he gets on the horse, and she says, but whatever you do, don't get off the horse. You can see where there's this leading. Actually, this is a more difficult one. There are certain bodily functions which would probably require you to get off the horse. But yeah, so he goes back and he's helping some people move some stones for a road, and the horse stumbles and he jumps off the horse, and when his foot touches the ground, he turns into an old man and he dies. These stories are similar. I believe that there's a story in the Quran of the same sort. Now, these are stories, ancient stories, part of our human and spiritual legacy that talk about traveling forward in time at different rates. Now, actually, strange as this might seem, traveling forward in time at different rates happens all the time. In fact, it's an intrinsic part of Einstein's theory of special relativity, in which someone who's zipping along very fast will have his clock tick faster than his friend who is looking at her clock on the ground. And this is something that is seen all the time, actually, in physical experiments. So these ancient stories are actually, in some sense, physically accurate. Probably physically accurate in terms of the warnings about, don't open the box, don't get off of the horse, etc. But I'd like to talk to you today about going backwards in time. And in fact, the possibility of going backwards in time is allowed by the laws of physics, as we'll see in just a second. And in fact, it's an open question about whether one might actually be able to build a time machine and go back in time. But I will tell you today about what we know scientifically about this question. And of course, once again, there have been many works of literature and art that have come before this, and that have sorry, let's see if I can get back to this, and that in some sense presage the various scientific theories that we have. And I'll also tell you, not just so you know that this is not just some theory, not only did my colleagues and I create a new theory of how you might travel backwards in time, but we did an experiment, which is the moral equivalent, if you like, of sending a photon backwards in time and having it try to kill its former self, which is an instantiation of the famous grandfather paradox. And not to give it away, but let's just say that when we had the photon try to kill its former self, in this experiment, you know those movies where at the end of the movie they say no animals were harmed during the making of this movie? You really can't say that about photons and our experiment. Okay, so these are my notions of PowerPoint slides, by the way. PowerPoint is a tool of Satan. It should never be used by scientists. It was made for business people to try to convince other business people of things that aren't true. So it's not really, hey, yes, but life is too short for bullet points, I say. Okay. So let me start with a bad PowerPoint joke. So time, as we know, flies like an hour. Oh, and all this is important because in all of the pictures, my own personal PowerPoint pictures I'm going to show, time always goes upwards. So this comes from in science you often see time going from left to right, or sometimes from top to bottom in electrical engineering. In physics, it actually goes from right to left for a bizarre reason. But in anything that talks about the universe as a whole, gravity, general relativity, and we're going to be talking a lot about that, it always goes from bottom to top, which I think is a kind of a lovely thing, the notion of time kind of growing like a tree. So as we know, time flies like an arrow and fruit flies like a banana. So this is my only PowerPoint joke. There, good. Okay, good. So enough of this silliness. The stories I was telling before are stories about going forward in time at different rates. And if you actually look in the past, look for human stories about going backwards in time, that's not as common. These stories are more recent. Maybe one of the most famous ones is Dickens's story, A Christmas Carol, in which Scrooge is taken back to look at his past self by the angel of Christmas past and Christmas present. But he doesn't get to interact with his former self, so it's not really a time travel story. But it's not really until the end of the 19th century, in particular with the very famous story by H.G. Wells, The Time Machine, that we get the notion of traveling backwards in time. And this is a story, it has all the ingredients that now are required for these stories. There is a time machine. Here's a person getting into the time machine. She gets inside, she dials up the time she wants to go, the red light goes off, and when she gets out of the time machine, she exits in the past, in this case to the embrace of a rather happy-looking dinosaur. I don't know what happens next, but can't be good. These stories about journeying to the past, they always end in tears. There's a famous story. The Time Machine, of course, is a very famous story, but then there are many other time travel stories. There's a famous story by Ray Bradbury called The Sound of Distant Thunder. Who here has read this story? Yes, a bunch of people have, yeah. So Sound of Distant Thunder, this gentleman goes into the past, back to the Jurassic area, and he vows he's not going to change anything at all. And he gets out of the time machine, and instead of meeting a dinosaur, he accidentally steps on a butterfly. Yeah, the butterfly effect, it's like, figures, okay, everything is fine. He goes back to what he thinks is his present day, and he finds that things are weird, the language is a bit different, politicians are acting very strangely. Well, that could be completely normal. And he realized that because of the butterfly effect, the sensitive dependence on this tiny event in the past, it has changed everything in the present. We'll talk a bunch more about time travel narratives in a bit. And actually, I'm going to ask people to volunteer some of their own favorite narratives, because we're going to discuss in these narratives there are different kinds of time travel, and the physical theories about how time travel could take place reflect these different kinds of narratives. So, now, lest you think this is all just, stories by Charles Dickens in the Mahabharata, in Japanese folk tales, and by H.G. Wells and Ray Bradbury, it is in fact possible in Einstein's theory of general relativity. This is Einstein, as you can obviously see. Everybody recognizes him. In Einstein's theory of general relativity, it is actually possible to have time travel. So let me remind you about how general relativity works. Einstein's notion of general relativity says that gravity, the force of gravity, which keeps us bound to the Earth, is actually a question of geometry. It comes from the curvature of space and time. And if you look at the global positioning system, GPS, which consists of a bunch of clocks, remember time goes up here, so these clocks are moving as they go here. This clock is ticking, 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 and this is the same clock at a later time. Here's another clock ticking, 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 going later in time, and this clock has gone around the curved edge of this curved-looking universe here. And they're sending signals back and forth to each other and determining when the signals left this clock and when they arrived at this clock, when they arrived at this clock, back and forth. And by putting all this information together, you can map out the geometry of space and time. And this is what GPS does. Actually, the global positioning system is so sensitive that it maps out directly the actual curvature of space and time in the vicinity of the Earth. For example, the master clock at NIST ticks very slightly slower than these clocks on satellites that are moving through space. And that's because the master clock at NIST is actually accelerated. I know it seems strange to think of it. It's sitting on the ground, which means the ground is pushing up on it, so it's accelerated, so it ticks slower. Now, this is all very well and good, and there's nothing in this that requires time travel. So, for instance, in this little universe, it's curved, as it's shown here, but it's got a rather orderly progression of time. Now, all this was very well and good from when Einstein started off the theory of general relativity around 1912 or something like that, until 1948. And in 1948, Einstein's friend, Kurt Gödel, of the famous Gödel incompleteness theorem, which shows that because of natural paradoxes like the Cretan liar paradox, which says, no matter what I tell you, I'm lying, which you probably already figured out, right? Because of these paradoxes, that there's a natural incompleteness and paradoxical nature to all of mathematics. Anyway, Gödel was having health problems. He was getting kind of obsessive-compulsive. He was always obsessive-compulsive. And his shrink told him, Kurt, you just got to work on something else for a bit. Stop it with this obsessive, incompleteness theorems, etc. Work on something else. How about, talk to your buddy Einstein over at the Institute for Advanced Study. Why don't you work on general relativity for a change? Gödel said, oh, yeah, that's a great idea, great idea. So he taught himself general relativity. Einstein and Gödel used to go walking around, they're fellow refugees in the Second World War. They'd walk around the grounds of the Institute for Advanced Study. And one day, Gödel comes up to Einstein. He's been thinking about general relativity. And he says, Albert, I came up with the most amazing thing. In a very rapidly rotating cloud of dust in the universe, then the curves that clocks follow actually curve around upon each other and return to where they started. So you can have what's called a closed time-like curve. So a space-time where you can go back in time and encounter your former self. Apparently, Einstein thought this was the worst thing ever. He was really, really pissed off. His beautiful theory of general relativity, marred by time travel and closed time-like curves. Well, I think Gödel was kind of happy, you know, and his shrink was probably annoyed. It's like, gosh, I tell him to go stop worrying about self-contradictory, paradoxical things, do something like ordinary by look at general relativity, and what does he do? He constructs a weird, bizarre, self-contradictory, paradoxical theory of general relativity. So, yeah. He killed himself shortly afterwards. It was sad. No, it's true. But for a different reason. Okay. So you have to ask them, if you have these closed time-like curves, if they actually really exist, and Einstein's theory of general relativity says they do exist, then what happens on the ground? What happens if you actually traverse one of these closed time-like curves? So you're in your spaceship. Sorry, I'll go back to this picture from Gödel. You're in your spaceship, you're moving along, let's say you're moving along something like this, and you go around this closed time-like curve, and then on the distance you see a spaceship. And the spaceship looks strangely familiar. And indeed, the spaceship is your spaceship in the past, about to enter into this closed time-like curve. So what the heck happens then? Okay? And the answer is, I don't know, but one has to deal with this question. So actually, there are some there's some great versions of this. So now the question is, since at bottom things are quantum mechanical, they obey the laws of quantum mechanics, how do you deal with quantum mechanics in these situations? And so about 25 years ago, my colleague David Deutsch, less well known, but for those of you who have met him, you'll realize this is an extremely faithful likeness of David Deutsch. For many years, I would see him, and he would only meet me at night, so I thought he was actually a vampire. But I did see him during the day once, and he did not turn to dust. So David Deutsch asked the question of how we can make sense of closed time-like curves at the quantum mechanical level. So in quantum mechanics, now's time for the brief course in quantum mechanics. How many people here have had a course in quantum mechanics, have studied quantum mechanics? Quite a few, yeah. You got to be careful in this area. Like it's like a well-educated crowd. And how many have not studied quantum mechanics? Okay. How many both have and have not studied quantum mechanics? Okay, right, there we go. All right, the true quantum mechanics out there. Got a lot of them. That's right, that's good. Good, we're in good shape. So, let me just remind you how quantum mechanics work. So, the idea is that things like waves, like the waves of light in this laser pointer right here, actually consist of particles. So waves of light are made up of particles called photons, particles of light. So for instance, if you were to attenuate the lights in the room so there's almost no light at all, then our eyes would still be detecting individual flashes, which are single photons which are being absorbed by our eyes. In fact, our human eye is well able to detect individual photons, individual particles of light, but in fact, in our optic nerve, there is this machinery that prevents it from registering in the brain unless there are 4 or 5. Otherwise, even in pitch blackness, we'd be seeing flashes of light all the time. Actually, frogs don't have this mechanism, which explains something about frogs, maybe. So, and similarly, particles, things like electrons or atoms, have waves that are associated with them. And you have this funny feature called wave-particle duality, which sounds completely weird, and it is. Indeed, this is the primary feature of quantum mechanics is its weirdness. Niels Bohr famously said, anybody who can contemplate quantum mechanics without getting dizzy hasn't properly understood it. And he even said it in Danish, which was even more impressive, right? So the idea about wave-particle duality is that if you have a particle here, then it has a wave that's localized over here. And if you have a particle there, then it corresponds to a wave that's localized over there. Well, that doesn't sound too weird. I mean, maybe that makes some kind of sense. But the problem here is that you can have a wave which is here and there at the same time, and this means that the particle in some bizarre spectral way is both here and there at the same time. Indeed, this looks like some bizarre animal, like maybe some strange version of Schrödinger's cat or something like that. So if you think of this as a bit of information, so electron over here is 0, electron over there is 1, then this electron here and there at the same time is somehow a quantum bit that reads 0 and 1 at the same time. Actually, the very first notion of time travel in, I've got to make sure my students tell me I have a tendency to tell stories that then get distracted from the point at hand, but this is a good time travel story. So, and it's really the first one about quantum mechanics and time travel. So, and you can verify that what I'm saying is true by looking at Feynman's Nobel Prize acceptance speech. So Richard Feynman was a very famous physicist, and in his Nobel Prize acceptance speech, he tells the following story. He says, I was, one day, so Feynman did his PhD at Princeton under the supervision of Johnny Wheeler, who was actually, I think, the same age as Feynman. But so Feynman says, one day, Johnny Wheeler called me up from the Institute, and he said, Feynman, I know, for some reason everybody always calls Feynman Feynman, though his name was Dick, I don't know, maybe so. I know why all electrons have the same mass. And Feynman said, really? And Wheeler said, yes, and I also know why the positron, the anti-electron, all have exactly the opposite charge of the electron. And Feynman says, you got to tell me, you got to tell me. So Wheeler says, well, it's very simple. So electrons and positrons are always created in pairs. Remember, time goes up here. They're always created in pairs. And they're always destroyed in pairs. So really what's happening is that there's only one electron, and it's going forwards and backwards in time. And so when it's going forwards in time, it's an electron, and when it's going backwards in time, it's a positron. So of course it always has the same mass and the opposite charge. And Feynman says, I thought this was the craziest thing I'd ever heard, but I stole the idea that the positron is an electron going backwards in time. And indeed, that's in fact how I learned about positrons in my first class on quantum electrodynamics, is that positrons are electrons going backwards in time. So David Deutsch came up with a notion of how you can think of closed time-like curves. So let me describe this picture. This is about as technical as it gets. So remember, time goes up, at least on this side. And this is ordinary stuff where time's going forward to it. Over here, there is a closed time-like curve where something goes backwards in time. So over here, time is going in the opposite direction, still vertically, but the opposite direction. And in between the stuff that's going around the closed time-like curve and the ordinary stuff can interact right here. And so Deutsch's criterion for making a mathematical theory of this is that the state here, as you enter into the closed time-like curve, assuming for the moment that the dynamics in this closed time-like curve is trivial, so nothing happens except going backwards in time, that is the same as the state here. So that when you enter, sorry, I'm having a little trouble with this laser pointer. When you enter into the curve here, you're in the same state as when you exit the curve there. Does that sound reasonable? Yeah, it sounds reasonable to me too. It sounds reasonable. So Deutsch made a particular mathematization of this, and the nice thing about this is it gives you a self-consistent theory of closed time-like curves. And that's great, but the problem is that the theory is weird. It's weird. All kinds of strange things, as we'll see in just a second, that you think probably shouldn't happen, can happen in this theory. And the reason that I got involved in this business is that one of the strange things that can happen is that you can use these Deutschian closed time-like curves to solve very, very hard computational problems very easily. we'll see that this is actually a feature of these kinds of closed time-like curves in general, that you can do stuff that you shouldn't be able to do, maybe not surprisingly. So I got involved in this field about 5 or 6 years ago because I had to referee a bunch of papers on a dispute about how these closed time-like curves behaved. And I got disgusted by this dispute. And I said, this is terrible. These people are muddying the waters. I think I could do a better job of this. This, by the way, people talk about motivation in science, and usually in books about famous scientists, it's like, oh, they have this pure motivation. They just want to understand the universe, and figure out what's going on. But actually, disgust at what other people are doing is a very strong and powerful motivation and should not be discounted as a good scientific motivation. It's like, I can't believe they did something so stupid. Of course, the same people are saying that about you, but what the hell? Anyway, so I went to my colleagues and I said, we can do something better. So let's do it. So I had an idea of what to do. And so we came up with an alternative theory, and you can see I have lots of colleagues here. These are both theoretical colleagues and also a whole bunch of experimental colleagues here, because once we came up with this theory, which we call closed time-like curves via post-selection, or PCTC, I'm the founding member of the IHA, which is the I Hate Acronyms Association. Anybody can join if they want. I'll tell you in a little bit what post-selected closed time-like curves are. But there's a long and nice history going behind it, and this is an alternative way of how you could have time travel. And so now I'm going to try to explain how this works. And this is going to be, we have a fair amount of time. So I will now explain, 1, quantum teleportation. Yeah, everybody knows about quantum teleportation, happens every day. 2, I'll explain how you can use quantum teleportation to escape from a black hole. This could be a very useful kind of thing. Jerry Sabloff, who's sitting over there, was saying how he was having this just terrible airplane experience the other day, and couldn't we do better about constructing better quantum teleporters so he didn't have to fly from place to place, but he could sort of teleport from place to place. So the real application would not be quantum computing, but quantum commuting. Right. Though I should warn you that in the current versions of this, that you might not want to be the first person to do it. On the other, people get into Google self-driving cars. I'm not sure why, but okay. And finally, I'll show you how this can be used. How this gives you a theory of what happens in these Gödelian, Einsteinian closed time-like curves. So. Are there any questions by the moment? Now, where this is like the halfway point? Do people have objections? I probably should object to everything here, right? Am I speaking sufficiently clearly and slowly? Can people understand me? Is it good? All right, a gentleman asked me to try to do that, not to mumble. So, okay, all right. Okay, well, good. Well, then I'll just keep on going until one of the time travelers from the future whom I invited to come to this lecture makes me stop, or not. Actually, time travelers from the future are notoriously closed-mouthed. They don't give it away. It's part of being a member of the society. Okay, so how does quantum teleportation work? Now, most people are here who actually, from people in this, how many people have seen Star Trek? Okay, yeah, amongst my students, my undergraduates at MIT, some of them have never seen Star Trek. Can you believe that? Star Trek has been off the air for a decade now, and you only see it in reruns, and many of them actually have not seen Star Trek, which I actually don't understand how they could possibly admit them to MIT without having them see Star Trek. It should be a prerequisite. I mean, what's going on? What do they teach children in schools these days? Anyway, sorry, no, excuse me. Okay. So in teleportation, the idea is Kirk gets into the teleporter. There's this dazzling flash of well, not very dazzling flash of kind of fake special effect light. He disappears, and then if all goes well, he reappears in the other teleporter in the other place. Of course, if things go wrong, you create two versions, the good Kirk and the evil Kirk, and then they can duke it out, and which happens more frequently than one might like. So this is actually possible to do. In early versions of quantum mechanics, in the first discussions of teleportation in terms of quantum mechanics, people said, it can't be true, because in quantum mechanics, when you look at something, when you measure it, you mess it up, and you get some probabilistic result, and the result is you've really disturbed things by a very large amount, and people thought it wouldn't be possible to teleport. But around 1990, almost 25 years ago, a bunch of people figured out you could do this, first in principle, and then very shortly, within a few years, in practice. And the way it works as follows. So remember, time goes up. Here is Alice, and over here is Bob. So all communication protocols have to do with Alice trying to send information to Bob. This is some time-honored tradition. It probably dates back to the ancient Greeks. I'm not sure. By the way, if someone's listening in, that person is always called Eve, for eavesdropper. And my wife, Eve, objects to this. So the way this works is Alice has some state, unknown state, psi. And the fact you can tell it's a quantum state, it has these funny little bracket things around it. This is actually how you quantize things. You make them quantum mechanical. You take something that looks perfectly classical, like the Greek letter psi for the unknown, and you put these funny little brackets around it. So for instance, at Google Research, the quantum group at Google Research is Google, but with funny little brackets around it. So now you know, this is very easy. You don't have to know anything about other than how to. The other way is to take things and to substitute a Q for it. So the other thing they could have done is called it Krugel. Okay. Now the idea here is that Alice and Bob may be very far from Alice, but long ago they shared what's called an entangled state. Entangled states are states that have a funny feature that if Alice makes a measurement on her part of the entangled state, it looks as if she's changed Bob's part of the entangled state. She hasn't actually, but entanglement has a kind of a funny quantum mechanical form of correlation that looks as if at first you could send things faster than the speed of light. You can't, in general, in ordinary quantum mechanics, though of course in just a second we'll be using this feature to do exactly that. Because as I've discovered that every elementary school child I've ever talked to or asked a question knows, if you can travel faster than the speed of light, you can also travel backwards in time. Who here knew that? Yeah, who you can travel faster than the speed of light? You can go backwards in time? Who here didn't know that? Okay, some people seem to be in a very, very quantum mechanical state here. In fact, almost everybody seems to be in a very quantum mechanical state here about that. That's fine. Okay. So then over here, Alice takes her half of the entangled state together with the thing she wants to teleport. She makes a funny measurement, onto a set of these funny entangled states. She gets, in the case of a single quantum bit, so she wants to send one bit of information. The measurement has 4 possible outcomes. She sends, which we'll call J, it could be 0001, 1011, so 2 bits, she gets 2 classical bits. She sends these 2 classical bits over to Bob. And then Bob does some transformation of his half of this entangled state. And when the dust is cleared, it turns out that he has exactly the same thing that Alice was trying to teleport. So you see, this is really very much the way that things work, that things work in Star Trek. So Alice and Bob have a shared resource. In Star Trek, there's a teleporter here and a teleporter there. They have to be connected by having this entangled state was prepared before. Well, that's fine. You had to send the teleporter down to the planet that you want to teleport to. Then you make some measurement which completely dematerializes the thing you're trying to teleport. And the interesting thing about this measurement is it completely destroys any information that was in the state, psi, that she's trying to teleport. So really, psi is completely dematerialized. And then you send some classical information over to the other teleporter, the place you want to teleport it to. Something happens over there, and then you reconstitute the thing that you want to teleport, and it exists over here. Now, in actual experiments, you don't have to send the actual matter and energy there. You can just get away with sending information, which leaves you with a problem of, like, what do you do with the matter over here that's been completely turned into what they call gray goo. This is called the gray goo problem. Could be hard, like, of course you can use it to reconstitute other people and you're teleporting people back, but it also could be, maybe we could use WIP for this. This would be a good thing. Okay, sorry, I know, I shouldn't joke about WIP around here. Okay, are people okay with this? Everybody's okay? Okay. Okay, good. People are nodding this. Yes, as Chris mentioned, I'm a professor of mechanical engineering, which means I need feedback. If I don't get feedback, like, I just go crazy, rampaging robot. Anybody unhappy, really unhappy about this? So good. That's good for you, sir. Okay. I didn't say you could ask a question. I just wanted to know if you're unhappy. I'm glad that you're unhappy. That's good. Okay. So now there's a funny thing here. So let me go back to this case. So remember, Alice makes this entangled measurement, and she either sends 0, 0, 0, 1, 1, 0, 1, 1. And then Bob does something over here. But in one particular case, this is the 0, 0 case, where the result of her measurement is actually this funny entangled state phi. She tells Bob to do nothing. She says to him, let me go back to the teleportation. She says to Bob, in the case where she gets 0, 0, she says, don't do anything, you already have the state. So with 1 out of 4 times, Alice sends the information to Bob, says, hey, you already have the state, no need to do any transformation, everything is fine. Okay? And I'm just going to draw this in a suggestive fashion in this next slide, that here she got this state phi, this other entangled state, and Bob does nothing. And in this kind of picture where I draw entangled states in this funny fashion before, I was mimicking this before with the electron and the positron. They're created in pairs like this. So you could think of this right here as the creation of an electron-positron pair. And you could think of this as the destruction of an electron-positron pair. And now you see that this Wheeler idea about time travel goes like this, that really what's going on is that in this one case where Bob does nothing, that this unknown state of this electron here goes forward in time, reverses, turns into a positron going backwards in time, and then reverses again, becomes an electron going forward in time and makes it over here. So in this one case, then this is just like this case that Wheeler had described in his telephone call to Feynman, that the electron goes forward in time, including all its internal information in the electron, goes forward in time, reverses, becomes a positron, goes backwards in time, and then reverses again, becomes an electron, and goes forwards in time. So it's the same thing, not only the same electron, but the same information contained by the electron going forward and backwards in time. And that's a perfectly okay way to think about how teleportation works, in particular in this one particular case where Alice makes the measurement and gets the result 0, 0. Okay? So are people by and large okay with this? You still unhappy back there? Yes, good. All right, good. Awesome. Okay. You can probably recruit other people who are unhappy. I bet other people, this shouldn't, I don't know if you should make this feel happy about this. Everybody should probably feel a little queasy about this, okay? Yeah, I mean, reversing direction in time is all worse than just spinning around really rapidly. But this is a perfectly reasonable way to talk about how things might go forward and backwards in time. And this is the basis for how you escape from a black hole. So, or at least one theory of how you escape from a black hole. So let me describe this. This is the so-called Horowitz-Maltesana mechanism for black hole evaporation. The idea is the following. Here is the black hole. So now I've drawn the same thing here, but here is the this black stuff is the part of the black hole. So this line right here is the horizon of the black hole. Our unknown state psi falls through the horizon, the point of no return. Nothing can supposedly escape from a black hole classically. Even if you're going faster than the speed of light, you still remain inside the black hole. Once you're inside here, you go at the speed of light, which is shown right here, you still stay in the black hole, and you get smushed to nothingness at the singularity of the black hole, the center of the black hole, where all known laws of physics break down. Now, you might think this is bad, like the all known laws of physics break down. A, you're being smushed to nothingness, and B, all known laws of physics break down. But in some, to physicists, or at least to theoreticians, this is an opportunity, because since nobody knows what the hell takes place inside at the singularity of a black hole, you're allowed to postulate anything you like, right? This is Horowitz and Maldacena took advantage of this. So they said, hey, suppose that we had some entangled states out here, and suppose that being smushed to nothingness at the singularity of the black hole is like this measurement in teleportation, which yields the result 0, 0. Then, if we have these entangled states out here, and this measurement is this is like this funny entangled measurement, then our information on this electron, let's say, can fall into the black hole, get smushed into nothingness, but then instead of actually being smushed into nothingness, what's happening is it's reversing direction in time, emerging backwards out of the horizon of the black hole and escaping off to infinity. And because, you can't get out of a black hole going forward in time, but going backwards in time, everything gets out of the black hole. So it's kind of good. And the great thing about this is that, in fact, these funny entangled states exist, because that's exactly what Stephen Hawking made his most famous contribution. He showed that at the horizon of a black hole, there's Hawking radiation, which are these particle-antiparticle pairs, like an electron and positron. They're being created out of nothingness. Ordinarily, in ordinary space, they go back into nothingness. But at the horizon of a black hole, one of them falls into the black hole, and the other one then goes off to infinity. And the way that you can conserve energy, have zero energy, is that the thing that falls into the black hole has negative energy, and so it decreases the mass of the black hole, and the thing that goes off to infinity has positive energy, and so the black hole gradually evaporates. It loses energy, its mass decreases. Is that insane or what? I remember when I was, I think this was like Hawking published this in 1973, I was 13, and I read about this in Scientific American, and I said, this can't possibly be true. Yeah, but apparently, at least something like this outside the black hole is taking place, and this is actually a pretty reasonable picture of how you might escape from a black hole. So actually, I know, it's bizarre, but what the heck. By the way, some people might say, gee, but suppose I fall in the black hole in my rocket ship, how about just like trying to reverse the rocket and go as fast as possible in the other direction? Now, the funny feature about that is, remember how the clock in NIST that's being accelerated ticks slower? If you're in your rocket ship and you try to accelerate going out of the black hole, you still get sucked into the singularity, but your clock ticks so slowly it looks like it happens faster than if you'd done nothing at all. So the advice I have to you is, if you fall into a black hole, is don't struggle. It's like quicksand, and also you better hope that something like this mechanism is actually going to go on, because otherwise you're in deep doo-doo. Okay, so in our theory of time travel, this is exactly what goes on. So we have, let me just go back to here. So we have this situation right here. You get measured as if you were this funny entangled state. And what that means is, not only is the state up here the same as the state down here, but the state back here is the same as the state psi. Moreover, even when this is the state psi, the state back here in the past is still that state. So if this mechanism works, then you can actually go backwards in time. So the way it works is, you have these entangled states down here. You have this kind of measurement-like process up here on its entangled state. And what that means is that the state here ends up being exactly the same as the state here. So it's a bit like David Deutsch's theory, except in our theory, this state here and the state here retain all their memories of everything else, this normal stuff. This is a Greek letter rho for the stuff that's normal stuff that's going in and interacting with the thing going through the closed time-like curve. So our theory differs from David Deutsch's in that this state here retains the memory of the future universe from which it left. Okay, so this is like Deutsch's theory, which I think is a perfectly reasonable theory. Our theory is well-defined. It's based on teleportation. It's really like teleportation to the past. So you dematerialize a thing here, and you rematerialize it over there, but instead of rematerializing it over there in the future, you rematerialize it over there in the past. And that means you can now look at what happens in things like the grandfather paradox, which is the ostensible title of this talk, where you can go back into the past and interact with your former self. So our theory gives a very detailed physical prediction, or rather retrodiction, of what happens when you go back into the past and interact with your former self. Moreover, as we'll see in a second, because our theory is based on teleportation, and because experiments like this can easily be performed, we can actually do a teleportation experiment and see what would happen if we sent something back into the past. And it's rather simple. We do the measurement. We might get many different results, but in the one case where we get this result 0, 0, then everything else in the entire experiment is exactly the same as if this particle, this electron, had gone backwards into the past. So we can actually do an experiment that tests what our theory says about various paradoxes like the grandfather paradox. So our experiment is actually if you like, the moral equivalent of sending a photon a few billionths of a second back into the past and having it try to kill its former self, as I advertised before. So let's look at what happens. So what is the grandfather paradox? The grandfather paradox is a famous paradox of time travel. The time traveler goes back into the past. She meets her grandfather when he's a young man, before he's had any children, and she kills him. He has no children, and he certainly has no grandchildren. So she doesn't exist. So she can't go back into the past to kill him because he doesn't exist. So of course then he exists. So he has a child who has he has a grandchild, and she exists, and she goes back in the past and she kills him. And how do you make sense of this weird double loop? I don't know. It's a paradox. That's why they call this a paradox. But both David Deutsch's theory and our theory actually have a prediction or retrodiction about this. So the way we set this up is we write this out in terms of quantum computation. We're going to do this as essentially, we use our little small quantum computers that we can build in the laboratory using photons and nonlinear crystals and entanglers and communication systems, and we set up a logic circuit that makes this happen. So let me just describe what happens here. So here is a single photon. We say that being 0 is dead and being 1 is alive. And this little thing right here, this little doohickey here, is called a controlled knot. And what this does is if this is 1, it flips this bit right here. And if it's 0, it leaves it alone. So the key point about this grandfather paradox is this loop right here. So the idea here is that this is a knot operation which takes a 0 and turns it into a 1, and a 1 and turns it into a 0. So what it says is if you're a 1 here, so if you're alive, you go around this closed time-like curve, and then the knot operation makes you dead. It turns you into a 0. So, but hold it, you were supposed to be a 1 here, so how could you be a 0? It also has the salutary feature that if you're dead here, so if you're 0, you go around it, it turns you into a 1, so it makes you alive. This is the part of the grandfather paradox that's not as frequently emphasized. It has this bad health health features for grandfathers in terms of killing them, but it also brings people back from the dead, which is a nice use for time travel. If you can, maybe we can get Obamacare to get this to pay for this. So what we do is we make a circuit and we monitor what happens. We say, okay, what this bit is going to read is it's going to say, if this is alive, if you see what this controlled NOT operation does, if I have a 0 here, and either a 1 or a 0 here, then it will just copy that value here. So if this is a 0, then this will become a 0, this will stay a 0. If this is a 1, then that will become a 1. So what all this circuit is doing is monitoring what the state of this time-traveling quantum bit or photon is doing. And the question is what comes out there. And what happens is the following. So in Deutsch's case, in the Deutsch version of time travel, what happens is if I'm a 1 here, then I always end up, so if this is a 1, so I end up being a 1 here, then what happens is over here I always end up being a 0. And if I'm a 0 here, so if I'm dead, then over here I'm always alive. Which means that the time traveler always manages to kill her grandfather. But what happens in our theory, and also in the experiment, is that if I'm alive here, then the time travel, then I'm also alive here. And if I'm dead here, I'm also dead here. So the time traveler never manages to kill her grandfather. What happens is kind of funny. So in the experiment, I'll show you a picture of that in just a second. You have something called a photon gun, actually. And the time traveler points her photon gun. I'm going to use my happy and old friend Chris Moore as my grandfather, and that's okay. He kind of looks, if he had a beard, he'd look a bit like the guy. So what happens is the time traveler takes out the photon gun, and she aims the photon gun at her grandfather, and the gun goes off, and the bullet's going towards him. And if the laws of physics were the ordinary laws of physics, it would kill him. But what happens is a quantum fluctuation whisks the bullet out of the way at the very last minute. And so my grandfather turns out to be a tough guy to kill. I wouldn't want to kill Chris. Actually, if it were my grandfather and I went back to see him in the past, I'd probably want to buy him a beer rather than kill him. But I'm not sure why people always want to seem to kill their grandfathers and these kinds of things. So there are two different, this is the difference between two different types of time travel narrative. So in one, which is true, for instance, the time machine or the this Ray Bradbury story, or for that matter, Back to the Future, or for that matter, Hot Tub Time Machine, I'm told, though I haven't seen that movie. You go back into the past, and you change the past. So the time traveler kills her grandfather. And when she does, she enters into a parallel universe, which is an alternative future. So in this first type of time travel, you go back into the past and you can change it and enter into an alternative future, a parallel universe which is different. So in this first kind of time travel, you can change the past. We'll call that type 1. Now, our version of time travel, if you go back into the past, then no matter how hard you try to change it, you fail. So this is also a type of time travel narrative, less common because it's harder to make happen. So a nice example of this in movies is the Terry Gilliam movie 12 Monkeys. Who has seen 12 Monkeys? Okay, great. Perhaps the most famous version of this is Harry Potter 3, Prisoner of Azkaban. Yes, a beautiful version of type 2 time travel. You know, Harry and his wizard buddies are hanging around Hogwarts. Weird stuff starts to happen. And they're going, what the heck is going on? And then as the book continues, then they figure out that, oh, what's happening is that they themselves, from the future, are coming back to the past and make the weird things happen in the past. So when they go through it the second time around, they realize, oh, this is me. Now I understand what's happened. It was me changing the past in this weird and strange way. Actually, what typically happens, if you try to go back and, in the past, in this kind of version, type 2 time travel, you go back in the past, you try to change something horrible in the past, like that terrible blind date that you had when you were 17, then what happens is you inadvertently bring it to make it happen. That's the normal terrible irony of this type 2 time travel. So our version actually implements this type 2 time travel. This is also what obeys what's called the Novikov self-consistency principle, which means you can't change the past, you idiot. Don't even try. Okay. So I'm out of time, but let me finish up with the second major paradox of time travel. We're looking for a set of the experimentalists who did our first time travel paradox experiment had a great time, and we got a whole bunch of publicity, but then in the end they realized that maybe it wasn't such a good idea. And so when we asked them to do the second experiment, they didn't do it. So anybody out there who wants to help us with the second experiment, by all means identify yourself. So in the unproved theorem paradox, the time traveler sees a beautiful proof of a theorem in a book. And she goes back in the past, and she shows the proof to a mathematician. This resembles several mathematicians I know. They're kind of cool dudes, they got goatees and stuff like that. Anyway, he sees this proof. He says, wow, that's a great proof. I'm going to include it in my book. And of course, the book is the same book in which she read the proof in the future. So the question is, who proved the theorem? And the answer is, no one proved the theorem. And so then what the heck is that about? Paradox. There's a more R-rated version of this, also phrased in terms of grandfathers, in which the time traveler, now a man, goes back in the past, meets this beautiful woman in a bar, they have a few too many beers, and they have unprotected sex, and she has a child who is the man's mother. And so he is his own grandfather. Right? And the moral of the story is, don't have unprotected sex. Exactly. Like use those condoms, please. I give this talk at high schools occasionally, and I think it's a very important thing to remind people how important this is. Particularly if you're traveling backwards in time. I think this is really key. But at all times. So I claim that this R-rated version of the grandfather paradox is this unproved theorem paradox, because if you think of it, because each one of us inherits a quarter of our DNA from each of our grandparents, this man inherited a quarter of his DNA from himself, and so a quarter of his DNA came from nowhere. It was never acted on by natural selection. It was never processed in any way. It's like the unproved theorem. So actually, in order to deal with this, David Deutsch actually throws up his hands. He says, this is terrible when we have a situation like this. Oh, and by the way, I think we have a picture of this circuit. Well, this is the logical circuit right here. What happens is, here is let's see, how does this work? So, I don't know. Okay, so, okay, here she reads the proof here, and then this is, so this is the proof right here. She reads it from the book, and then here she shows the proof, which gets sent back into the past, and then it gets read right here. Still looks a little weird for me. Like, I don't understand this stuff. Like, this, one of the secrets of working on this quantum computing things and doing quantum mechanics is, how Niels Bohr said that quantum mechanics is weird and counterintuitive. It never ceases to be weird and counterintuitive, no matter how much you do it. You just kind of get used to it. So you get used to being dizzy all the time. So the question is, what happens? And in David Deutsch's case, he says, I don't know what happens. So he says, it's just got to be randomized. The proof just has to be made into something random. So he says, we're just going to inject randomness into this to make it random. And in our case, what actually happens is something very interesting, is that you end up constructing a wacky entangled state up here, which also effectively allows the proof to be, in this case, proof is just a single bit. It could be 0 or 1, but it allows the proof to be both 0 and 1 at the same time. Because nobody decided it should be one way or the other, it ends up being both 0 and 1. So it kind of equitably chooses all possible values at the same time. Okay, so, and this is an experiment, as I say, this is an experiment we can do, and we will do it as soon as we find an experimentalist who is willing to risk his or her reputation by working on time travel. So, Oh, and this, by the way, this is the, I'm now done. So this is a picture of how the experiment works. I think the main thing you can see, it's hard to read right here, but here is this part of the experiment, which is the quantum gun, the actual quantum gun or photon gun. This is actually the name for the thing that we use to try to kill our grandfather photon in this case. And by the way, what happens in our case, right, is that the photon that goes back into the past and tries to kill its former self, even though gajillions of photons are destroyed in the course of this experiment, the photon that goes back in the past and tries to kill itself always fails, no matter how hard it tries. It points the quantum gun at its former self, pulls the trigger, bleep. But in the end, as the experiment shows, in the end what you find is that this is, I'm not going to explain what all, this is just to show you that we did the experiment, right? This is like, what do they say in Gilbert and Sullivan? And a pleasing air of verisimilitude to an otherwise bald and unconvincing narrative. But what we find is that the photon never ever manages to kill itself, but what happens is that the probability of actually measuring the right state as the quantum gun gets closer and closer to trying to kill the photon, our probability of actually being able to perform the experiment to see the photon going into the past goes to 0. So, let me just conclude that by saying time travel is a really remarkable topic. Human beings have been thinking about travel for time probably for as long as human beings have been aware that time existed, and certainly for many thousands of years, dating back to our earliest human narratives. Time travel actually appears to be consistent with the laws of physics. We don't know if this is true or not, but Einstein's theory of general relativity allows the existence of closed time-like curves, and normally in physics there's a rule which is anything that is allowed is mandatory. No, it's true. So if it's not forbidden, then you can do it. And so under that circumstance, it's important to actually try to figure out from the laws of physics how time travel might work. People have been doing this now for, since the 1940s, for more than half a century. So ever since Gödel figured out that Einstein's theory allowed time travel, and Wheeler and Feynman started talking about particles and electrons going backwards in time. There's been a lot of work on this done by people like Kip Thorne, who wrote some really great papers about this in the 1980s. And more recently, my colleagues and I realized that maybe we could actually do something about it. And of course, what we tried to do is send a photon backwards in time and have it try to kill its former self, and luckily, it failed. So, okay, let's not worry about the future, because the future will take care of itself. That's the end. Thank you. All right. So I'm sorry I went over, but we have time for questions, and let's have people ask questions. I saw you over there, so please speak up loudly, and I'll then repeat the question.
Einstein himself famously found that quantum mechanics extremely weird. In fact, he never fully reconciled himself to it. He once said that to believe in quantum entanglement, you have to believe in spooky action. So my question is, if we teleported Einstein to the present, the alternative with quantum mechanics, would he reconcile himself to it?
Okay, so the question is, Einstein, I think, was pretty clear, but I'll say it again. So Einstein never really believed in quantum mechanics. He called things like entanglement spukhafte Fernwirkung, which means spooky action at a distance. And the question is, what would happen if we brought Einstein from the past to the present to ask him this question? I actually have an empirical version of this, because I used to live, when I was in the 1980s, I was a graduate student living on the Lower East Side of Manhattan at 2nd Street and Avenue B, along with all the drug dealers and people there. And I was at our local Polish coffee shop, and this homeless person came up and sat next to me at the counter, and he turned, put his arm around me, and he said, "They took Einstein's brain and they transplanted it into my head." This is true. And I said to him, "Wow, this is great. I'm a physicist. I've been wanting to ask you all these questions." But I'm afraid to say that from our conversation, the operation was not a success. Yes, sir.
How do you deal with entropy if your time travelers are multi-particle organisms? You'll have disorganization as time goes on. When you reverse time, how are you going to get that organization back?
Yeah, this is a very good question. So the question is, how do you deal with entropy? You know, entropy is randomness in the motions of atoms and molecules, and the second law of thermodynamics famously says that entropy increases. So the randomness in the motions of molecules increases as time goes on. And so if you go backwards in time and show up in the past, and entropy is increasing in the past, how do you deal with that? Well, you know, shit happens, you know. However, yeah, so because that is actually a very, very perceptive question, so in fact, our theory, and Deutsch's theory as well, so in Deutsch's theory, the way it gets dealt with is that entropy increases at a much more rapid rate than you'd expect to mask any possible increase of entropy in this closed time-like curve. It's a kind of a problem for his theory. His closed time-like curves are just spewing out vast quantities of entropy, which just actually makes some kind of sense if they're, you know, if they come out inside black holes or something like that, because black holes are famous for increasing entropy. And in our theory, what happens is that you in fact do end up decreasing entropy, but not in such a way that allows you to do things like, you know, make perpetual motion machines or anything of that sort. So, so it is something you have to deal with, and we have an answer, but neither Deutsch's answer nor ours is very satisfactory, I'd say. Yes, sir.
You didn't mention Groundhog Day.
Yeah.
So in Groundhog Day, in your loop that goes around, as you pass the horizontal line, if you're the same when you pass it as you were at the beginning. But if you learn all these stuff that's going on in the box, you're not the same.
Right.
Every time you go around and you learn something, the information is different. So in Groundhog Day, finally you figure it out because you keep changing, so you're not the same before the line as you are when you go.
Right. So the question is, in Groundhog Day, it seems you seem to change every time you come around. And so in that great Bill Murray movie, then it is indeed true. That is a classic example of type 1 time travel. So every time he goes around and wakes up in the morning, his alarm clock goes off, and he finds himself at the same time, the same place, but in a slightly different universe from the one he was in previously. So he's kind of cycling through this set of parallel universes, ending up finally in one that's satisfactory. So Groundhog Day is a great example a very nice example of a type 1 form of time travel. Yes, sir, in orange. Am I okay? All right. So the question is, let me just paraphrase your question. So Hugh Everett was the scientist in the 1950s who formulated the many worlds theory of quantum mechanics, which says that there are all these parallel universes out there in quantum mechanics. And indeed, David Deutsch's theory, is a type 1 theory of time travel. And what it says in time travel, you exit your branch of your world, your Everettian world, and you enter into a parallel world. Actually, David Deutsch and I encourage you to David Deutsch and I had a debate in Wired magazine, actually in Hot Wired was the first online magazine back in 1998 or something. If you look around on the web, you'll find this about the many worlds theory of quantum mechanics. I'm not anti-Everett, but we just came up with our theory, and we didn't know whether it was type 1 or type 2 version of time travel. It was only after we came up with the theory and worked it out could we actually figure out that it was this funny type 2 version which enforces self-consistency. I mean, I don't really take a position on whether these other worlds actually exist or not. I only know that my world is the one that I care about, like, you know, the one where Chris and I are going to go get a beer after this lecture. So is there someone from over there? Yes, sir.
If the electron turns into a positron,
Oh, that's a good question. So the question is, if the electron turns into a positron as it goes backwards in time, does that mean the electron slows down before it does so? I guess so, because it's got a reverse. I don't know. Yeah, yeah. That's a good question. I don't know. Yes?
So, if you go back 2 slides, you showed a curve comparing the predictions of your theory with the measurements done in the experiment.
Yeah.
And I noticed that there are several regions of the curve that don't agree with your experiment, or the experiment doesn't agree very well with your theory. Can you explain why that's the case?
I think that if the experiment agreed exactly with the predictions, then you should be very, very suspicious. Yeah, in fact, you may notice that even here, the theory predicts that a number, which is basically a kind of a probability here, should be less than 1. I think this error bar means it is higher than 1. So this is a number which is a probability which is higher than 1 according to experiment. So yeah, anytime you see experiment exactly agreeing with theory, you should be very, very suspicious. Yeah, thanks. Yes?
This is not a good question, but
Well, could you sit down then, please?
can you name a couple of practical examples that I can take home and tell my friends that this applies to in my life or in some other
That wasn't a good question. As I already told you next week, for God's sake. Look, I mean, this is not very practical. Our experiment, I would like to emphasize that our experiment is not constructing a time machine. For that, you'd really need some kind of wacky, like Gödel-like universe, or have a couple of interacting black holes in order really to create a closed time-like curve. What our experiment does is because the problem is really, if you go back to if you go back to the banana fruit flies, in our experiment, what happens is, in order for it to really function, you'd have to have the red light always go on. But what happens in our experiment is that maybe a quarter of the time the red light goes on, and when that happens, everything is exactly the same as going back in the past. So this would not be a very useful time machine if you wanted reliably to go back in the past, because 100% of the time you're dematerialized in the present, and only a quarter of the time you end up back in the past, and that's kind of a bummer. But maybe at a kind of like a larger level that at least at the level of science, I mean, this kind of shows you that it's worth actually trying to take ideas like time travel and seeing if you can't actually do them in real life. I mean, in terms of, getting from here to work in the morning, for that we need quantum commuting via teleportation, right? But in terms of at least thinking about what it might mean to travel in time, I think we have to come up and look at something like this, which is a bad answer to your bad question. Yes, sir.
I posed a question to Ed Whitten back at Princeton about my definition of time as a distance between two events in space. Without a blink, he said, "What do you mean by distance?" So I would like to ask you if you could define time. Don't describe it, just define it.
Define time. Well, in terms of measuring time, that we can do, because actually we define time as a second, and a second is defined as if you look at the time it takes a particular hyperfine level in a cesium atom to oscillate back and forth some, around 10 billion plus or minus times. People with an iPhone can tell me how many that's the definition of a second. So time is defined in terms of clocks to be in terms of physical processes such as oscillations of atoms. And that's very useful because it also gives us an operational experimental way of defining time. Yes?
Your theory references post-selection.
Yeah.
Post-selection element.
Yeah. So let's see. So, okay. So we call, you can think of our theory as post-selected teleportation. And what does it mean post-selection? So in ordinary teleportation, Alice and Bob have this entangled state. Alice wants to teleport psi. She makes this measurement. She gets 4 possible results, 0, 0, 0, 1, 1, 0, and 1, 1. And then she sends off this result. Bob does something, and he gets the state back. That's how teleportation works. What our theory is mathematically equivalent to is taking only the results where Alice gets 0, 0, post-selecting those, so selecting only those results. And rather than saying, okay, rather than those occurring with probability a quarter, say that it always occurs that way. So this is why what we're doing is not actually building a time machine, because if you actually do the experiment, what happens is, a quarter of the time you get 0, 0, quarter of the time you get 0, 1, 1, 0, 1, 1. And we post-select, after we've done the measurement, those outcomes. This is a well-known technique in all of experimental physics for saying, well, what would happen once you get a particular outcome? So you just simply say, we only get a particular outcome per experiment. So that's what post-selection means in this case. Yes, way there in the back. Yes, you. Well, now that is a good question. Yeah. So go ahead. Did you finish? So the question was, did human beings create time to organize things, or did they discover it? It's such a good question that I can't even answer it. So though I must say that if humans created time in order to organize things, then they did a spectacularly bad job of the organization part. Yes, at the end. The question is, did time start at the Big Bang, and if so, what was there before? The answer is we really don't know. So current evidence, both theoretical and experimental, suggests that the Big Bang, which is a gigantic explosion that occurred everywhere, maybe looking a little like this, was preceded by an epoch of what's called inflation, where the scale of the universe doubled every tiny fraction of a second. Now, in these models, it could be that the universe actually started, and before that there was nothing. Or it could also be that this had been going on forever. So the second kind of model is called eternal inflation, in which this kind of process of inflation had been going on forever before the Big Bang. And we really don't know the answer to that. I certainly don't. And actually, even my friends who are really real cosmologists don't know. Sorry, yes, you
So how do things like Hawking radiation and quantum entanglement, does that affect the dynamics and evolution of galaxies?
Well, yeah, so the question is, in general relativity, which governs the gravitational behavior of big things like galaxies and also supposedly small things like atoms, and also things like black holes, how do these funny quantum effects like Hawking radiation affect things like galaxies? Well, probably in the level of galaxies, not very much, which is good, because if people really don't understand how general relativity and quantum mechanics get put together. No, I don't think that you need quantum mechanics at that level. Quantum mechanics is very important for studying the dynamics of stars, star formation and the histories of stars, but for galactic dynamics, probably not. On the other hand, for black holes, I think it's important. And black holes, it might even be possible to make them in the laboratory, though I rather doubt it. And when we started these experiments about time travel, we didn't want to, we wanted to build a real closed time-like curve, which we could do by having two rapidly moving black holes moving past each other. But when we actually ran this by the workplace safety people at MIT, they nixed it. Like, the fools standing in the way of science. Oh, sorry. I went into my mad scientist mode. Yeah. So. Yeah, thank you very much. I think we can talk more afterwards, but thanks very much. Thank you, Jerry.